So welcome to Math 389 Advanced Analysis. So this is an entire set of slides for today. So one of the things that's nice is as you go further in your career, you have the chance to personalize things a little bit in terms of what you want to study, what you want to learn. So there are some things that I think everybody should be aware of, and everybody should know. But you have related but not necessarily identical interests. And one of the things I want you to be able to get out of this class is to pursue things that you love. This is a writing intensive class. So what this means is you will be doing writing. There are two types of writing that you can do. One is the writing that goes into the recycle bin at the end of the semester that nobody ever looks at again. And then there's the writing that other people read. And by other people, I don't mean me, your professor, or your graders. I mean people in the real world. I like to write books. I like to write a lot of books for undergraduates. I think it is not necessarily a great idea to write books for undergraduates without extensively talking to undergraduates, as they will be the ones reading the book. So there are lots of opportunities to work on books that I'm writing. So I have 3 books right now. One of them is already completed and being reviewed. One of them is maybe half done, and one of them is maybe 1/6 to a third of the way done. And so one of the ones that I'm really excited about is this book on operations of order, talking about when are you allowed to do things that you want to do? When can you just play fast and loose with the mathematics? When do you have to worry about the order of operations, and when do you not? And so that is a wonderful opportunity for writing. I'm also working with a colleague of mine on a book on L functions and sphere packing. Sphere packing is one of the most important, both pure and applied problems right now in mathematics. It's incredibly difficult to prove optimal ways to pack things. And there are applications in this in terms of information transfer. So there are a lot of opportunities to work on stuff like that. I also want people to be working on math outreach. Is depending on who you're talking to, you write in a very different way. You do not use the same tone of voice and the same word choices with a 5th grader as you do with your thesis advisor. Out of curiosity, how many of you are at least considering a PhD in a math or allied field? Well, if you go like this, then you're at least considering it, right? So then your hand has to be up because you're considering. Okay, so most of you are at least considering such a career. This means you have to learn how to write well. You should have 3 versions of your thesis that you can give depending on who you meet. If you meet an expert who works in your field, you should be able to have a high-level conversation. If you meet somebody in the general area of mathematics, you should have a different conversation. And if you meet somebody who controls funding, you have another type of conversation for them. One of my favorite authors of all time is Isaac Asimov. Prolific writer, designs a universe where basically the mathematicians take over. And it's hard not to like somebody who creates a galaxy ruled by mathematicians, if all works out. I mean, but he also has a PhD in biochemistry. And as he was getting ready to write his thesis, he realized, I've got to write in this dry scientific style. I haven't been writing like that. I've been writing engaging work. I got to practice. So he decided to write a fake scientific article. And has anybody heard of this story? So he created this compound called thiotolumine. And it dissolves in water, like a lot of compounds do. But based on how confident you are that you will add the water, it dissolves that much earlier before you add the water. It has a negative time to dissolve. Hopefully everybody can realize that you have enough chemistry that this is absurd. He had fake journals. He drove the librarians in New York crazy because people were going to the libraries trying to find these journals with these studies that he completely made up. And so he told Campbell, who was his main editor, that, I just don't want to publish this under my name. Oh, yeah, that's fine. I don't want people to think I'm making fun of the field. That's fine. It's a wonderful, funny article. And so, of course, Campbell publishes it under his name. And there's stories as to whether or not he did this deliberately or he just forgot. Fortunately, Isaac Asimov had friends who have his back. I hope you all have friends who have your back. And when his fellow graduate students discovered this, they quickly bought up all of the copies of the magazine around the institution and hand-delivered it to every professor in the department. So Isaac Asimov is just absolutely in dread as he's getting ready to take his oral defense for his thesis. and the professors are grilling him, and then the last question is with a straight face, somebody says, can you describe some of the thermodynamic properties of thiotolene? At which point he realizes that professors are actually human beings, they have a sense of humor, everything is fine. But he practiced that, and it's a very different way of writing depending on who the audience is. I want you to have exposure to many different types of writing. I want you to have high-level writing, and I want you to have more math outreach that's designed to excite people who don't have the same background. So you will be doing some of each. I have no problems with people working in groups. I would like people to be presenting to the class about things that you found interesting. These are great skills to have. I don't want to insult anybody, so you do not have to speak up, but if you are thinking about being a professional mime, please raise your hand. Okay, if you're seriously thinking about being a professional mime, please raise your hand.
I was wondering where this was going, and no one was raising their
Yeah.
hand.
So I have never had a student say that they were seriously considering a career in mime. Not that there's anything wrong with a career in mime, but I've yet to have a student say that they want to be a mime. What distinguishes math and stats from all other departments in terms of graduation requirements? Not an oral exam, but close.
The talk.
The talk. We are the only department that still requires you to actually speak before we let you graduate as a major.
No, CS also.
Oh, does CS require it?
Yeah,
Okay,
CS
I was
also
told
has
that they
a
did.
little
Okay. Did you just have to go? So you actually, okay, good. So there's two departments.
Yeah.
All right. Now, CS, of course, is an offshoot of math. I mean, they used to be part of it. So, I got to be careful because this is being recorded. They're, of course, a completely independent, autonomous. But I actually, last year, one of the CS professors ran a small group as well. So,
yeah.
I will correct, most departments do not require a public talk. Most people are not going to be mimes. You are going to have to talk to people. You are going to have to communicate. And depending on who you're talking with, it's a very different argument that you construct. If you are giving a 5-minute talk, that's very different than a 50-minute talk. I have been in places where they believe in the 4 parts of a talk. The first part is accessible to grad students, the second part to professors, the third part to the speaker, and the fourth part to the Almighty God. And the 4 parts are not split equally. And very quickly, you reach the point where nobody understands what's going on. I was once in a talk about functions f such that f log squared f is in L2, and what consequences this has for the Fourier series expansions. This was probably the most hyper-technical talk I have ever been to. As this is being recorded, I will leave it at that. Okay? You have to know your audience. You have to pitch your talk based on this. I want you to have useful skills, and I want you to have things that you can show at the end of the day so that when you're applying for things, you can say, here is some work that I've done, and here is how it's been used. So I am the president of the Fibonacci Association. I cannot just redefine the golden mean. I don't have that kind of power, but there's a lot of things I can do. I'm one of the managing editors of the Fibonacci Quarterly. We have a math outreach section. A lot of natural stuff to do. The very first article in the Math Outreach section is co-written with an undergraduate who's at Williams right now. And this is going to be a wonderful thing that she can put on her CV and resume that she was involved and you were going to have a social media blitz on this. I want you to be able to have something accessible that you can point to. When you are applying for grants or for jobs, you need to be able to distinguish yourself. One of the things that is often very important is broader impact. How are you helping the community? Newton is famous for saying something along the lines, I can see so far because I'm standing on the shoulder of giants. A lot of us have a desire to give back. And so I want everybody to do something along those lines. At the same point, this is also an upper level math class. I want you to see good advanced mathematics. I want you to learn how to write things carefully, rigorously, and well. And I want you to write things that are worth writing. So, in the beginning, there are a couple of topics I'm going to lecture on. This is, to some extent, an opportunity to try to fix some, I'll say, omissions in your math career. That you might have gotten to a point where things were not fully rigorously done. Okay? In terms of the actual mechanics for the class, I am very open to how we do this. This is not a large class. We can fit into this room. it's small enough that we can personalize it based on what you want to get out of it. And it doesn't have to be a one size fits all. Everybody here, I assume, knows calculus. Okay, in a calculus class, if I don't teach integration by parts, I have failed, right? You can't leave calculus without. Well, actually, in the 21st century, you can, because nobody ever does integration anymore by hand. Everybody just uses Wolfram Alpha or some other program to just do the calculations. But in lower classes, there's certain standard material that must be covered. In upper level classes, we often have a lot more freedom. When you go in grad school, whatever topic you choose for your thesis, you are basically committing yourself, if you stay in academia, to working in that field for several years. Not just as a grad student, but beyond. It's a publish or perish environment. You've spent all this time becoming an expert. You really need to keep going and get more papers. I want to use this as an opportunity for you to explore, to see some good mathematics. This is advanced analysis, not advanced algebra analysis. So my bias is towards analysis. However, there are a lot of times where you can't do analysis without knowing some algebra or some geometry or other fields as well. And so I'm absolutely open to, hey, I want to push it in this direction. Is that okay? Absolutely fine. So, again, there is a lot of flexibility. So I'm going to ramble for some amount of time today. There will be no class on Tuesday to give you time to just think about what you want to get out of it. And so I am canceling class for a variety of reasons. I really want to drive home how important it is for you to think about what you want to get out of it and give you the time to do so. Not just 5 minutes. I'm going to give you the entire class time. You don't have to come into this room and think unless it helps you. But think about what you want to get out of it. I'm also going to be out of time. But I mean, for my probability class, I'm going to zoom in and I'm going to do my probability class by Zoom. We could have done that as well, but I really want you to think about what you're going to get out of it. You don't have opportunities like this all the time. And so let's try to figure out, what do you want to get out of the class? Can we make that work? And if so, then this is going to be great and wonderful. And if it's not, then it's better for you to figure that out early in the semester that this class is not for you. I know people have different backgrounds and people have taken different classes. And so if you've seen complex analysis, one of the things we will do is I will show you my proof of the Riemann hypothesis. As this is being recorded, I know the proof is flawed, okay? But I just only do one small illegal thing. And so that's one of the points of the book that I'm writing, this, operations of order, that there are so many things that are true most of the time, but occasionally not. And one of the goals is to help you learn about these occasionally nots. All right, so in terms of the mechanics, every now and then I might give you just a few homework problems to do just because it's good to do homework problems occasionally. That's not the point of this. The point of this class is to write things and to write things well. That means iterate. You can write in groups, you can write individually. Everyone's going to do at least one outreach and at least one high-level thing. And you're going to write things that will be read by other people. Hopefully, I'll be able to get you comments in real time from editors. And so I will always record when we meet in person in Zoom. And then if there is ever anything important that we need to talk about off the record, you can always hit the comments. So you could always just hit, pause recording if there was something you wanted to say that you didn't want recorded. But, fortunately, none of us ever have anything like that because we're always open books. So, for this class, in terms of the actual mechanics, we'll have some lectures, especially in the beginning, but a lot of it is going to be smaller individual meetings where if there are things that you're unclear about, I will help you with, or if a bunch of you want to learn the same subject, I'll give some background lectures on it and then we'll go further. And then, just try to find things that excite you. And I have no dearth of things that excite me. So it shouldn't be hard to find something. And in terms of math outreach, there's a lot of things that I have over the years that I think would make wonderful articles if people are interested in converting them. So again, I want you to have two complementary skill sets as you leave this, writing for extremely different levels. And I want you to use this class as a springboard to investigate things mostly on the analytics side that excite you. So my brother is an engineer. I am able to talk to him, but it's sometimes very difficult because we do math very differently. Good engineers, good physicists, they can play fast and loose with the math. And what they do can be justified. They're also sometimes a lot more concerned with how quickly it can be done. And your efficiency of algorithms is huge with them. So what I want to do now, and some of you may have seen me give some of these lectures before, and if so, I apologize. I want to just get some sense of where everybody is and what background you have. So I'm going to give you three functions. F of x is, let's say, x squared, x to the 3/2, and x to the root 2. What are the derivatives?
Are we gonna just say the answer?
Yeah.
Oh,
Everybody, you can say one answer and then somebody else has to speak up. So you get to go first because you've spoken. I'm going to put you on the spot.
oh, 2x.
2x, okay. Anybody want to continue? Yep. Everybody want to do the last one?
Square root of 2x, x to the power of square root of 2x.
Excellent. So hopefully everybody is able to do that. Yes. So in my classes, please email me whenever you make a comment. And just at the end of the day, just shoot me an email and say, hey, Professor Miller, here are the comments I made in class today. There's several reasons for this. One is it helps reinforce the material because it forces you to remind yourself what did we talk about in class. Second, it gives me, I maintain a data sheet of non-trivial comments to make about you if I ever have to write a letter of recommendation. I'm the director of the William Small REU, which means I get to deal with all the paperwork. No one ever wants a job like this. Yeah. I also lead a group, which is a lot of fun. That I love doing. The paper, no, I don't like the paper. I read a lot of letters of recommendation, and you sometimes get letters of recommendation that are, so you've just said that what's in the transcript is correct. You just said that they were a student in your class and they got the grade that the transcript shows. This gives me nothing. You want to make sure you get to know at least one professor well each semester. It doesn't have to be me, happy if it is. Always happy to meet and go for lunch, grab a coffee, go for a walk, go to a .com, whatever. And you get to know you. But you want to make sure at least one professor gets to know you every semester. That way, if you're only successful half the time, by the time you graduate, 3 or 4 people will know you well enough to write letters of recommendation. And I know too many people who sadly do not know enough professors to write letters of recommendation. As an aside, you want to make sure you don't go to the ridiculous extreme of having too many people write letters of recommendation for you. When I was a postdoc at Brown, I had my first experience with a helicopter parent. Some of you, I think, know the story. I was walking out of class one day with 2 of my favorite students and we're chatting. And one of my colleagues said, can you talk to a prospective and his mother? I go, of course. He then goes to his office and he writes me an email. Really sorry for doing that to you, Steve. I had to get out of there. We spent over an hour. The son was fine. The mother was crazy. If you haven't heard the story before, you are allowed to guess how many letters of recommendation she arranged for her son for college. To put things in perspective, does anybody remember how many letters they used for Williams, approximately? 2. Okay. Anybody want to guess how many she arranged? 10. Any other? 10.
Okay, well,
Okay, no, that's fine. 10. Okay. Okay, 10. Any other guesses?
8.
Why are you saying 8?
I don't know, a little bit smaller than 10.
Yeah, because the way I said it didn't make you think that 10 was overestimating.
I don't know, just based
Yo,
on
if I
visual
had
expression.
as few as 10,
Oh.
so again, you can
Disgusting.
manipulate people based on the words you're using.
Oh.
So we have 10, we have 8. Anybody want to make another guess? 15. So are you now thinking that it really was higher than 10? And I was.
We'll see. Maybe deceiving.
I do love deceiving. If you, I mean, it's being recorded, but maybe I'm deceiving about liking to deceive. No. If you take the 10, the 8, and the 15 and add them, it's lower than how many she had.
What?
She had over 40 letters of recommendation for her son. No, you're laughing. I see a lot of you laughing. I see some of you are very nice and are not laughing. Thank you for understanding just how serious this is in applying to school. And it might be that her son and the next applicant were tied in every category that matters, and they were starting to look at lower level categories, and they finally got to the point of tooth care. And that's where the letter of recommendation from the dentist would come into play, because he talked about his consistent flossing and good side-by-side, and she's proud of this. I'm not even going to get into how well he mows the lawn according to his neighbor. You have to reach to get to 40 plus letters of recommendation, okay? When you had this much, whatever good there was is drowned in the noise. So you want to be careful in terms of what are you writing, what are you putting? You can have something that's really good, and if you put so much stuff around it, people miss it. Part of doing a good job is knowing what not to include. All right, so we will really discuss in great detail how do you write things. Most math articles are very hard to read because the details are omitted. And a lot of my colleagues say if we put in the details, the argument looks trivial and then it's not going to get into a good journal. So you omit all the details. I wrote a great paper with some small students years ago. It was 50 pages. The published version had to be shortened to 20. I would never want to read the published version. We moved all the calculations for many of the theorems to appendices that were just on the archive version. So you could do something like that and have a longer version. In any journal that I work on, I try to allow long submissions and in fact encourage long submissions. Especially when you're writing books, you want to put in the details so that people can follow things. All right, so everybody remembers their basic calculus. How do you calculate the derivative? How do you calculate the derivative of x squared is 2x?
Well, by definition.
By definition, okay. So we're looking at the limit as h goes to 0 of x plus h squared minus x squared over h. And how do we calculate x plus h squared?
To expand things.
Okay, so we expand things, and what do we use to expand?
Well,
FOIL, first, outside, inside, last, or more generally, binomial theorem. If we looked at x to the 3 halves, we would have x plus h to the 3 halves minus x to the 3 halves over h. We can't use FOIL. We can't use the binomial theorem. So how many of you actually proved correctly what the derivative of x to the 3 halves is in calculus versus your teacher maybe did FOIL and pushed it and said, yeah, in general, the derivative of x to the r is rx to the r minus 1. So how many of you did not see this correctly? I'll put my hand up. I don't think we saw it correctly. It's really easy to sneak things by you. Okay. Anybody know how we could prove this limit? How we could calculate this limit?
Newton's formula. Is it not Newton's formula?
Okay, so to do Newton's formula, you need to be able to take derivatives.
You don't need to. I mean,
You're using Newton's binomial theorem, right?
Yeah.
How do you think Newton's binomial is that proved using calculus?
Oh, it's used.
So as an aside, what's the limit as h goes to as x goes to 0 of sine of x over x? Who knows what that who can calculate that limit? 1. And how did you do this? L'Hopital. You get 1. Everybody comfortable with that? You all fail. Disgusted. Absolutely. Oh, sorry. We're supposed to be positive and encouraging until ad drop is over. When is ad drop over?
2 weeks.
2 weeks. Okay, I can do 2. I can do 2 weeks of encouragement. That's a really good approach. What's wrong with using L'Hopital's rule? L'Hopital's rule means you need to know what the derivative of sine is. How do you calculate the derivative of sine? You need to know what this limit is. You can't use L'Hopital to calculate this limit because to calculate the derivative of sine requires this limit. Now, the limit is 1, but it can't be shown by L'Hopital. So you have to be more careful. So again, this is one of the things that I really want to stress in a class like this. We need to write things clearly and carefully. A lot of times, especially in lower level classes, things are more straightforward. You don't really have to worry. But as you go further, it is possible to have these hyper-technical things that will cause trouble. And one of the things I want to do is I want to emphasize this for you. So how would we calculate? Newton's binomial theorem would be wonderful, but we can't use it.
Like using Taylor series of science.
Okay, but to use the Taylor series, what do you need to know?
I mean, you can just.
You
take it
need to
as
know the derivative.
You can define the sign as in terms of the.
So if you define sine of x, so you can always define your way out of problems, yes. But I want you to get an appreciation of how difficult this can be. So does anybody know how we could actually handle the x to the 3/2? I know 2 ways to do it.
Yeah, I got away.
Okay,
I mean, we can first show the derivatives of all polynomials with integer powers, just using the binomial formula.
good.
Then using, like, defining, like, if you can get all rational powers by taking powers of those ones and then doing the chain rule on both sides.
Okay, so what function would I use?
So like, if you want to find the derivative of
X to the 3/2.
x to the 3/2, you say y equals x to the 3/2, then take square both sides. get
Okay,
y
so what I could do is I could say f of x is x to the 3/2. G of x is f of x squared, which is now going to just be x cubed. So g prime of x is going to be 2 f of x, f prime of x is 3x squared. So f prime of x is going to be 3/2 x squared over f of x, but f of x is x to the 3/2, and so it gives me 3/2 x to the 1/2.
Now, once you got rational exponents, you just have to do a.
Okay, so wait,
error analysis. Error
so we'll start with rationals for now.
Oh,
Okay. So that's one way to do this. That's the best way to do this, is to introduce this auxiliary helping function. And then we need to know essentially the product rule, or just the power rule, that f of x to an integer power, that's not too bad, we can prove that directly. There is another way to do this. So one of my professors mentioned that a lot of mathematics, Peter Jones at Yale, comes down to doing nothing. And there are 2 good ways we can do nothing. What are 2 good ways to do nothing?
Add 0, divide by 1.
Add 0, divide by 1. I've never heard divide by 1. Multiply by 1, multiply by 1. But you can't divide by 1. Divide by 1 is fine, right? So, and then he goes one day, the log of 1 is 0. There's only one thing you can do in mathematics. And so we could multiply by 1. Does anybody see how we can multiply by 1? What should we multiply? The conjugate, right? X plus h to the 3/2 minus x, I'm sorry, plus x to the 3/2 over x plus h to the 3/2 plus x to the 3/2. So when we do that, this is then going to become x cubed, I'm sorry, x plus h cubed minus x cubed over h, and then we'll have x plus h to the 3/2 plus x to the 3/2. So the bottom is looking a lot like h times twice x to the 3/2. Now, if x is equals 0, then there's some problems. So you have to do x equals 0 separately. So we're okay if x does not equal 0. If x equals 0, do separately. And so this would work for the exponent of 3/2. What if I gave you 3/17? Would it still work? And so I'll leave that as an exercise to see how far could you push this. Okay, so we've gone from integer to rational. Now let's try to go to irrational, like x to the root 2. So what would you say we do? Because you had big ideas a moment ago, so.
Oh, try to. We can just define a sequence of irrational exponents converging to the real one and try to switch the limits. And we can switch the limits because they converge already.
So now we need some kind of justification of order of operations. So we'll have the function f, say r sub n is of x, and maybe Rn is converging to the square root of 2. And then we can talk about how would you find a sequence of numbers that do that. For each one of these, we can take the derivative, and then we want to claim that the limit of the derivatives is the derivative of the limit. And you're going to do this with high school kids. So that is absolutely one approach. Another approach is to, and again, this is one of my favorite springboard problems. It's so easy to manipulate things and not even understand what you're manipulating. Does everybody understand what it means to calculate x squared? I'm taking a number x, I'm taking it again, I'm multiplying. I can do that. If I want to calculate the square root of x, I'm looking for a number y such that y times y is x. I understand that. What does it mean to raise something to the root 2th power? And so one way to handle this problem is to basically say x to the root 2 is e to the root 2 natural log of x, and use e to the z is the sum of z to the n over n factorial, n goes from 0 to infinity. If we use this as our definition of e to the z, and again, this comes back to how we're defining things, now all of a sudden, I'm only taking numbers to integer powers. I understand numbers to integer powers. And I can then use this in the chain rule to now calculate what's the derivative of x to the root 2. So the purpose of this exercise was to just show you how easy it is for us as professors to slip things by you. If you're writing a book, and I've had arguments with people, I serve on a national standards committee right now, where I have no trouble sleeping at night if we do not do things fully rigorously. But I do have trouble sleeping at night if we don't tell people that we're not doing things rigorously. I want to at least plant a flag and say, no, the proof used for x squared is not the same proof that you would use for x to the 3/2. And so a lot of it is to try to understand how far can you push an argument. So a lot of times, if I look at a special case, the argument for the special case may not work in general. One of my favorite results in all of mathematics is the following. At least one of e plus pi and e times pi is transcendental. Has everybody heard the phrase, what it means for a number to be transcendental? So you're algebraic if a root of a polynomial of finite degree and integer coefficients. L is transcendental. So for example, I would be an algebraic number because it's the root of x squared plus 1 equals 0. So either e plus pi or e times pi is transcendental. Anybody have any idea what might be a useful ingredient in the proof?
Like multiply or combine them in some way to get something which is the root of a polynomial, and then somehow one of e or pi is transcendental, and then
Well, do you know anything about e and pi that might be useful?
They're transcendental.
Well, we know they're transcendental, but they're not just two random transcendental numbers.
But e to the power of
I pi plus 1.
Equals,
Oh, equal to -1.
yeah, writing it like this, it's -1. You could also write it plus 1 equals 0. There's lots of ways of writing. This might be useful. Turns out, no. I don't need e and pi. It's the theorem is if alpha and beta are transcendental, either the sum or product is also. How many of you have taken an advanced algebra class? So in algebra, you might have seen that algebraic plus algebraic is algebraic, algebraic times algebraic is algebraic. So if this doesn't make sense to you, it's absolutely fine. The proof is if not, alpha plus beta and alpha beta are both algebraic. So alpha plus beta squared minus 4 alpha beta, which is just alpha minus beta, squared is algebraic. The square root of an algebraic number is algebraic. Therefore, alpha plus beta is algebraic. Oh, so this should be alpha minus beta. And then you get 1/2 of alpha plus beta plus alpha minus beta is algebraic. It's actually just a statement about if you have two transcendental numbers, either their product or their sum is transcendental. And most of the time, both will be transcendental. It's possible when you're given a problem, if you know things about it, you might prove a special case by using specific properties, and then that argument doesn't generalize. And so one of the things I really want you to be thinking about is when can you prove a special case with great ease, but maybe it's going to hurt you later on. And so a couple of years ago, I was running a small group and we were trying to extend something to several dimensions and it just wasn't working. And then said, you know, we're using the best results in one dimension. Let's go back to the very first paper in the subject, which proved a much weaker result, but using a far more elementary method. That generalized to higher dimensions very easily. And so, one of the things to be very aware of is when are you making assumptions that simplify maybe a specific case of the problem, but they could put blinders on you in terms of going further. So a big part for me for this class is the order of operations. Everybody here has taken multivariable calculus, yes? Can somebody remind me what Fubini's theorem says? Or the Fubini-Tonelli theorem, if you want to impress me.
So like if like a two variable function is absolutely integrable, then you can switch the two.
Good. So if the double integral of the absolute value is finite, I can integrate in either order. What if the double integral of the absolute value is not finite? We don't know. And so here is one of my favorite examples. So rather than doing a double integral, I'm going to do a double sum and show that the double sum depends on the order in which we do things. And again, it's just easier to do things as a double sum than a double integral. You can always smear things out. It's not a big deal. And I'm going to show that the sum over m, the sum over n of a m n is not the sum over n, sum over m of a m n. So we're going to define it to be +1, -1, and then 0 for the rest of eternity, 0, +1, -1, and then 0 for all eternity, 0, 0, +1, -1, 0 for all eternity, and so on. So if I do, first I do the columns, then the rows, what does every column sum to? 0. So if I do first columns and then rows, what do I get? So if every column sums to 0, I get 0. But if I do first rows, then columns, what can you tell me about the row sums? Every row sum is 0 except for the first, which is 1. So here's an example where the sum of the double sum order matters. We can't just willy-nilly change. And it turns out that as long as the double sum of the absolute value is finite, you're okay. Whenever you see infinities in mathematics, this is a warning sign that you have to be careful. And depending on how you do things, you can get lots of different results from infinities. Okay. Let's continue with some calculus examples. One of my favorite rules in calculus is the sum rule. So can somebody tell me the sum rule? So calculus, the sum rule for derivatives. Anybody know the sum rule? Everybody agree with this?
both are differentiable.
Okay. If differentiable. Is that what Bruce said? Who was listening really carefully? I'll admit I don't always listen to what you guys say. Did I write it down correctly or did I mishear him? I was trying to think if I wanted to use the same color, if I wanted to shift to blue because it's being added on to Ami's. So I apologize if I didn't write down what you said exactly because I was thinking about color. Is this what you said if differentiable?
Oh, if both functions.
That's different. There's a key word that I dropped. Well, there's nothing in the first line that says something about two functions.
Oh, sum. Oh,
So how many summons am I allowed to have? So is it infinitely many or is it two? Because you said both now. So when you said the derivative rule, are you thinking two or are you thinking infinitely?
I thought two because I thought sum is defined as two.
I mean, you can take the sum of numbers. And the way you would execute is you would execute it by summing in pairs. Summation is a binary operation, but we can definitely have sums of more than just two numbers. So are we talking about an infinite sum or finite? So for example, you prove for sum of two functions. Now consider the derivative of a plus b plus c. Is it okay for me not to write of x for each one of these? It's so nice to teach an upper level class. Okay, this is the same as let's group a and b together. And now we have a sum of two functions. And so this is now a plus b prime plus c prime. And now I can use the sum rule again because I just have two things. And now I can expand back out. So you're okay if it's a finite sum. And so as a nice induction proof, show that any finite sum of differentiable functions is differentiable, and the derivative of the finite sum is the finite sum of the derivatives. Let's consider, oh, I don't know. Yeah, it's tough to pretend ignorance. F of x is sum, and it goes from 0 to infinity of sine of n factorial x divided by 2 to the n. Does this sum converge? Yeah.
oh, sorry. I was thinking about the derivative, but yeah, the sum. Yes,
So why does the sum converge?
absolute value.
Yeah, absolute values. So this sum converges. I don't need to have anything as large as 2 to the n. I could have done n squared. That would have been fine. But as a general rule, give yourself some extra space. Don't try to live just on the cusp so that if something goes just a little bit wrong, you're dead. Give yourself a little, I'll give you myself some nice geometric convergence. What's f prime of x? And I'll put a question mark so you're not committed to it. What would you like to say?
N factorial cosine n factorial x over 2. But it doesn't converge.
So f prime of 0 would be the sum, and goes from 0 to infinity, of n factorial over 2 to the n. So exercise, show n factorial is greater than n halves to the n halves. And that's more than enough to show, or you can even show that it's greater than, say, 4 to the n if n is greater than 2025. And whenever you see something like 2025, I'm just being safe and not trying to figure out what's the smallest n I need to show that n factorial is at least, 4 to the n. So that's enough to show that it blows up. So we have issues with the infinite. So again, this class is supposed to be advanced analysis. It's to take a lot of the results you've seen and ask ourselves, what do we need to make this work? What do we need to be careful about? What do we need to be aware of? And so I want to give some lectures like this. Some of you I know have taken complex with me. When we did complex, I proved the Riemann hypothesis, right? Or did I have you watch that at home? Okay, all right. I'll prove the Riemann hypothesis then later in the semester. I mean, it's worth seeing a proof of the Riemann hypothesis if you haven't seen it before. Obviously, I'm going to be doing something illegal. And one of the purposes of this class is to train you so that you are aware of stuff like this and you note when you're doing it. It's so easy to make these mistakes, to implicitly assume that you're doing something that's right. Well, of course, the sum of the derivatives is the derivative of the sum. But we have to be careful. I am teaching a pre-core probability class, which means I can't go into full detail of everything. But if people here are interested in probability, I'd love to go into some of the technical details and show why complex analysis is needed and why you have to be careful. This is either one of the best functions in the world or one of the worst functions in the world. F of x is defined as e to the negative 1 over x squared. Yeah. So those of you who have taken a class with me before, you know this function, okay? If you plot this function, what happens to this function as you get closer and closer to 0? So if you've seen this function before, you can't talk. Hello? Yes? And I'll send an email later. So if you look at the plot of this function, it decays extremely rapidly to the origin. As an exercise, you can show that the nth derivative at 0 is 0. And here you actually use L'Hopital's rule. So the Taylor series of f is identically 0. But the function is not identically 0. So you have the ridiculous situation of a function that converges for all x. Its Taylor series converges for all x, but it only equals your original function at the origin, which is really not that impressive because the Taylor series is f of 0 plus multiples of x, which clearly vanish when x equals 0. You have to be careful. You can have the ridiculous situation where the Taylor series converges but doesn't converge to the function. So anyways, I hope this gives you a little bit of a sense of what the class is going to be like. I sadly have to go now, and I will shoot you an email and we can chat further.